Hello, greetings to all of you present here. Myself, Lalit Shukla, in the capacity of convener and host of this series, welcome you for the second session of this lecture series. This Frontier of Physics lecture series is jointly organized by Faculty of Physical Sciences, Shri Ramswaroop Memorial University, and Physical Sciences Consultorium. Shri Ramswaroop Memorial University is located in Barabanki district, close to Lucknow. Faculty of Physical Sciences offers a vibrant ecosystem and leadership in physical sciences. We offer undergraduate, postgraduate, and doctoral program in the department. Faculty of Physical Sciences is founded with the university in 2012, and our organizing partner, Physical Sciences Consultorium, is a consortium of experienced professionals to offer our expertise to academic institutions, industrial organizations, and newcomers to encourage innovation, build collaboration, and mitigate confusion. With this brief introduction of these organizing partners, uh, I would like to invite Dr. R.J. Singh sir, Dean, Faculty of Physical Sciences, Sri Ramswaroop Memorial University, for short welcome address to this gathering. So,
Okay. Thank you, Lalit. Thank you for inviting me to this lecture series, and uh, it's a very good initiative so that we can hear some real experts who are working in real physics nowadays. Okay, so on the behalf of Faculty of Physical Sciences, I am welcoming to our today's speaker, Dr. Sudip Haldar, in this lecture series, and he is the second speaker, I think, in this series, Frontier of Physics. So the topic is very interesting. I must say that's a very interesting topic that is exploring many body physics with Bose Einstein condensates. Well, I'm not an expert in this, definitely in this field, but from some basic statistical mechanics courses, what we know that BEC, I think, is the short form of this more popular. The Bose Einstein condensate is it's a state that appears at very low temperature, and it's also the fifth state of the matter. Also, some experts call it. And I think in nowadays, people who are working in quantum computer find this state interesting to perform certain. Uh, we will get some more knowledge about this state and the so Dr. Haldar for this talk. Please, Dalit.
and thank you, Aditya, for encouraging remarks and all guidance throughout this such initiative in the department. And now it is a great opportunity for me to introduce today's speaker for this session. I was really fortunate uh, at during my stay in PRL. I spent some time with our guest today's guest of the session. So for all the people who are joining in for the session, later on it will be available on YouTube. So for them, it is let me formally introduce to the speaker, Dr. Sudip Haldar. Dr. Haldar is currently working as assistant professor at SRM University, Sonipat, Haryana, which is in NCR, Delhi region. And Dr. Haldar obtained his PhD degree from Calcutta University in 2015, and after that he joined a prestigious physical research laboratory in Ahmedabad for postdoctoral fellowship. And during that, I got chance to interact with him for some time. And after spending about 2 years in the institute, he went to University of Haifa, Israel, for his postdoctoral uh, research, and he stayed there for about 3 years. And after that, he joined this SRM University and currently working there. He has he got several fellowships during his research work. He was he got CSIR JRF fellowship, Institute Postdoc Fellowship by University of Hyderabad, BK 21 fellowship from Seoul National University, and he has presented his work at several national and international forums and published papers in journals of international review. And he is also he is life member of uh, Indian Society of Atomic and Molecular Physics. So it is really great opportunity for all of us to interact with uh, experts who is working on the field, and so it is great opportunity for all of us. And I sincerely uh, thank him for his, uh, he, he makes time for us from his busy schedule. University, SRM University, Sonipat Haryana is currently working on this next cycle, so there's a lot of work in the department, and he managed time for us. So thank you so much, Sudip, for being here and taking time for us. And I'm sure that the students who will be joining the lecture, and later on those who are listening it on YouTube will surely get benefited. Our lecture series is basically intended to UG PG students of physics department, and in the end of the session we have a session. Yeah, we have a question answer session. So the people who are joining us on YouTube, they can write their question in comments, and I will take some questions depending upon the availability of time for this session. So we are we are like after these all the announcements and introduction to the organizing partners, I request to the speaker, Dr. Sudip Haldar, for the presentation.
Thank you for introducing me, and thank you to you and Dean sir for inviting me to this nice initiative. It's a great pleasure to be part of this initiative of Physics Consortium lecture series. And it's always nice to interact with young pupils and exchange ideas. So let me share my screen before I can start to today's. Hmm, wait, I think first I
Yeah,
have to, yes. So yeah. I hope my screen is visible to all of you.
yes, yes, the screen is visible to us.
Okay, great. So today I am going to talk about exploring many body physics with Bose Einstein condensate. As Dean sir was saying, Bose Einstein condensate is more or less well known to everyone who has got a chance, got an exposure to the physics. It's a very fundamental topics, and since my our primary target audience is the UG and PG student, so I have planned my talk in two different sections. There's two different sections. The section one is basically more like reviewing the basics of Bose Einstein condensations, basics starting from what we learn at the UG or PG level, and then covering what is the developments in recent past and how these things evolved, starting from the prediction of Bose-Einstein condensation by Einstein in 1924 until the observation of it in 1995 by the group of Anderson in MIT, USA, and then why people were so enthusiastic, why the degree of enthusiasm you can understand from the fact that immediately after observation of BC in atomic system, in ultra cold atomic system, we will talk about later, successive 3 Nobel Prize was awarded in this field. So you can understand from this simple fact the importance and of the field and the kind of enthusiasm people has about it. And so what is the, and then we will discuss that how it helped us to open new paths to explore physics, to explore problems which were hitherto not available to the experimentalists to study directly. And then next, in the next part, we will discuss about one specific, there are a lot of possibilities to study different problems with BC. It is a very popular test bed to study different problems, and because it's a very interesting system, it has a very we have a very great control over every parameter of this system. So you can really test many things experimentally with a with a uh, great degree of control. So out of that many possibilities, I will talk about one possibility, one direction of work which I have been working in collaboration with Professor Ofiri Alon, who is now Dean of University of Haifa in Israel, and we are part of a much bigger group of MCTDHB group, which is primarily based in the Heidelberg. Our main members and most of the team members are in Heidelberg, but other members are also spread over different countries. And my next project, I got what we are proposing, that I am going, I am just starting with in collaboration with Professor Aditi De from Harishchandra Research Institute, Allahabad. There we are trying to proposing it is, we already got a grant from DST to for this proposal to study the quantum entanglement in a many body wave function, which is basically the main ingredient for quantum information and quantum computation, quantum teleportation, and other quantum technologies. And again, these Bose-Einstein condensate and ultra-cold atomic systems provide us a test bed to test our theories and fine-tune it. So it's a very versatile system. So first thing is, the name is very interesting, Bose Einstein condensate. On one part we have Bose, Satyendranath Bose, who is an Indian scientist, and on the other side Albert Einstein, who is a giant in physics. It's one of the biggest star in the sky of physics. So how these two names came together, that's itself is a interesting story. After all, at that time, Satyendranath Bose was in Dhaka University. He was teaching physics, and this he was far away from the Western mainstream research community, and India was a colony, British colony. So how it happened? So as things stands, if we look at it from the side of the Albert Einstein, then he was working there. He was already well-known scientist. He has already given to us general and special theory of relativity, Brownian motion, and things like. So he is already well-known, very established chemist physicist. Now he was working and basically struggling to understand the quantum concept of light and subsequent Planck radiation formula. Around that time, suddenly he receives an letter from a seemingly unknown person sitting few thousands of miles away in a colonial country, who is proposing a completely new derivation of the Planck's radiation formula without mentioning about waves or whatsoever, and he is speaking completely in terms of light quanta photons. Basically, this derivation reduced the problem of deriving Planck's radiation formula into a problem of counting how many photons you can assign to a cell of energy h nu, so that total energy remains constant. To understand how this is the novel idea behind this derivation. And with the derivation, he directly wrote to Einstein. The idea, basic idea, if we try to understand, it's like this. So let me try to show you. Suppose I have two box, and then I have two ball. In one ball, let's call it, mark it with a cross, and in the other ball, let's mark it with the plus. Now the problem I ask, what is the number of possible states? How many way we can distribute these balls in these two boxes? The answer is 4. We can have 4 possibilities. Number 1, I can have the two ball here. Then the second possibility is I have one in this way. The third possibility is, and of course the fourth one is this one. So what is the probability that two balls are in each box? One box has two balls. That probability is basically 2 by 4, that is 50%, right? Now what Bose is proposing, that suppose someone erase these marks on the balls. So now what will happen? So if I remove that, so I will have now two box and two balls with no marking. So then what will happen if I again do the same problem? The possible states that I can have is now this one possibility, second possibility, and the third possibility. So now what is the probability that two balls are in a same box? Now that probability is basically 2/3, or roughly say 66%. So you see, the counting rule proposed by Bose favors a situation where particles are in the same state, and this is a general phenomena. It is applicable if you add many more balls and many more boxes. And recognized it. Einstein recognized this importance or the originality of this proposition, and he uh, immediately put a forward note. So basically what happened, after deducing the Planck's law in this way, in with the Bose distribution, Sothen Bose wrote a letter to Albert Einstein. He did not know the German well, so he requested Albert Einstein to read the paper, and if he finds it important enough, and then make an arrangement for publication. Let me show you a picture of that letter. Now, many times people like as famous people like Einstein gets many letters like these from different persons, and most of the time there is a good chance that people ignore such letter, because after all the sender is completely unknown, and the idea is also too revolutionary. But he was not a ordinary person, he was Albert Einstein. So he read the paper, he understood it is important, he translated it into the German, and put a forward covering letter on the importance of the paper proposition, and sent it and made it published in that famous journal of that time, Zoothpicks of Physics. After that, he followed it up, and he argued that the law, the counting rule, the statistics proposed by Bose, it's not that it is only applicable to photons, but it is followed by any material atoms, any atoms or particles of a gas, which are basically bosons. I will tell about it later. So both then but the problem, one basic difference is there. The photons, when we are talking about photons, if you reduce the energy, basically you reduce the temperature, so the energy will reduce, then the number of photons will reduce. But when we are talking about, say, helium gas and the atoms in the helium gas, then if you reduce, the number of particles should be conserved. So the distribution law, the counting rule, even though is very similar, but there will be a slight change in its mathematical uh, there will be a slight change in the mathematical expression. So in case of photons, I will have this 1 upon e to the power beta e minus 1, where beta is the 1 by kBt, kBt is the Boltzmann constant. But in case of a real gas, for example helium gas, I will have this extra term of mu, that we can understand very by considering that suppose you have a reservoir of helium gas, where you have helium atoms which carries a energy mu, and now you connected the reservoir with the box we are talking about, and you add the atoms from the reservoir to the box to a particular energy, then there will be a change in the energy. To do it, you need it cost energy, so the energy will be replaced here by epsilon minus mu. So this is the Bose Einstein distribution law, and the particles that follows this statistics is known as bosons, after the name of Schotten Bose. Basically these are the particles which has integer spin. Similarly, there are another kind of quantum particles, though they are known as fermions. They have half integer spin. They follow the Fermi-Dirac distribution. The basic difference between these two is that, as we already discussed, Bose distribution favors accumulation of atoms in a single state, whereas Fermi-Dirac fermions follow Pauli exclusion principle. So they are more lonely, they are not social. And so we are not talking about fermions today, we are dealing with the bosons. Now, once we have this distribution, so immediately Einstein understood the importance or the deep physics, deep significance in this distribution, and he wrote a further paper on it, and he showed that if the temperature is reduced, then this mu is actually increases from negative, from bottom to the zero. Here we are talking about ideal gas, a free gas, so the energy of the each particle, the minimum will be zero in the ground state. So mu goes to the zero, and that time this number of particles per unit state becomes infinitely large. Now, okay, ordinarily you may think that okay, it's a mistake, how can a physical quantity can diverge in this way, but Einstein understood that it's not a mistake, but something, it is representing something that is actually happening in a real gas. But inspired more than a decade after, nearly 14 years after also, we could not find any physical analogy of this phenomena. So much so that Fritz London in 1938 went on to comment in a paper that In course of time, the degeneracy of Bose Einstein gas has rather got the reputation of having a purely imaginary existence. However, in the same paper, London recognized that the superfluidity just discovered that time may be a manifestation of this Bose Einstein condensation. But liquid helium is not a ideal non-interacting gas. It's a liquid having a very strong interaction. The interatomic, when the atoms are very close, there is a strong repulsion. When they are far, there is a weak attractive interaction. So it's not the ideal gas. So you cannot directly apply the Einstein's concept to this system. And later, around 60 years later, it was confirmed experimentally that nearly 10% of the atoms are accumulated in the ground state in case of superfluidity. So to directly test, to directly have the Einstein's concept in experimentally, we need a system which will be much more closer to the ideal gas. So basically we need to study the Bose Einstein condensate in a gas, and there comes a difficulty. Now to understand that what is the condition that should be satisfied when we are talking of, if we want to achieve the Bose Einstein condensation in the gas, again let me show you. So basically what we will have now, suppose if we have a gas with the density n, then if we have the gas with density n, then the average interparticle separation will be n to the power minus 1/3. And at a temperature T, the thermal de Broglie wavelength is h by square root of 2 pi m kBT. Now, if the wavelengths of different atoms have to overlap, because to have the indistinguishability as a prominent feature in the system, it is important that their wave functions superpose with each other. So, it's necessary that the length scale of the system is of the order of the de Broglie wavelength, and then we must have this n to the power minus 1/3 of the order of lambda. That means n lambda q of the order of 1. To be precise, n lambda q should be, I think, of the value will be around 2 point something. I don't remember, 2.4 or something. But this is the basic condition. Now, how we can attain this condition? This condition can be attained in two possible ways. Either you use a system with very large number of particles, very high density, or you increase you reduce the temperature. Either way you can achieve this condition. But so actually in the neutron star and many astrophysical objects, the density is very high. There you can obtain the Bose Einstein condensation with a higher temperature. But here we are interested to study the Einstein's original proposition in the system his own concept experimentally. So we need a system which will be closer to the ideal gas system, that is, which is nearly non-interacting, that is the gas. So now here you, I think you already got the first hunch of the problem, that the problem comes that if we are talking about so we cannot increase the density, we have to lower the temperature. But as we lower the temperature, at low temperature the system turns into liquid and then solid with no more a gas. But we have to maintain the system in the gas. So as we are reducing the temperature, we must come with a technique to prevent this solidification of the gas. Now, here we have to understand how this solidification happens. So what happens when there are, when we will consider a gas, there are many particles in the system. Now two particles collide sub there, and there is nearby a third particle. So when the three particles collides, two particle can form a molecule, and the third particle can take away the extra energy or the binding energy released. So basically we need three body collisions for the gas to convert into liquid and liquid to solid. It's not necessary that only the atoms of the same kind is required for this three body collision. Even the container wall can help to exchange the energy required for forming the molecules. So first thing, we have to reduce the possibility of such three body collisions. One possible way is to make the system very dilute, so that the intercollision time period between the two collisions, between two three body collisions, becomes very large. And second is, we cannot use a physical container. We have to come with some different technique to confine the system in a region of space, and that is done by magnetic or optical traps. Another severe challenge at that time was to obtain the low temperature. Now, to have this dilute gas, the typical density comes around n to the power 10 to the power 13 to 10 to the power 15 per centimeter cube. And in for this density, the temperature required for Bose Einstein condensation is of the order of 100 nanokelvin. Now, around that time, we had no option to achieve such low cold temperature. Your normal refrigerator or cryogenic techniques will not help you. So new techniques were required, and those techniques, laser based cooling mechanisms and evaporative coolings, were developed over the time, which ultimately helped us to observe the Bose Einstein condensation. So you have to first choose a system for laser based cooling. An initial choice was basically laser based cooling or magnetic trapping. An initial choice was basically the hydrogen atom, hydrogen 1H hydrogen atom, and the main reason was that this hydrogen 1H spinol, that doesn't liquidify even at a very low temperature. But due to several technical challenges, this effort was not successful initially. Later, of course, it was observed, BEC was observed in this system also, but initially it was not successful. So there was a parallel effort by another group of scientists. They were trying to cool a system of alkali atomic gas like rubidium gas or lithium gas. Now the first success came with the rubidium. So here, if I talk about the technique, broad technique. So first thing, it was trapped by the lasers, optical traps and magnetic traps. So basically, and then it was cooled by lasers. Now, when we are talking about cooling, we have to keep in mind here the when we are talking the temperature is actually related to the kinetic energy of the atom. So cooling down the system, cooling down the gas, or means basically slowing down the atoms in the gas. So what we do here, we apply counter propagative laser beams from all the six directions. So now, as the atoms moves, it will be kicked by the photons of the incident lasers, and in each collision the atoms will lose some momentum. So it will lose some kinetic energy and slow down eventually, and that's how we are reducing its temperature. And the frequency of the laser should be in a way that it takes care about the Doppler effect. So when the atoms moves, the frequency that it sees and that is coming to of the laser beam that is coming to it, and the frequency of the laser beam that is coming from the behind, that has to be detuned accordingly. So, but the problem is, with laser cooling, you can achieve up to say, some micro Kelvin, but we need to go to the order of nano Kelvin. So here comes the another technique. This technique was also being studied by a different group of scientists. Initially, actually, when people were trying, they were trying all these cooling techniques individually, whether it is optical cooling, this Doppler cooling, or evaporative cooling. They were trying it separately to achieve the low temperature. But as it turned out that each of these techniques have their own limitations. For example, Doppler cooling works very well when you have low density. On the other hand, evaporative cooling works when you have a high density. So finally, people came with the idea of using both the cooling technique one after other. So they start with the Doppler cooling. As system cools down, basically it slows down. So in one area, the atom starts to accumulate, density becomes larger. At that time, they transfer the whole system from the optical trap to the magnetic trap, and then they apply the evaporative cooling. Now, in the what we mean by evaporative cooling, it's not the best concept is very simple. Like if you have a cup of tea with a hot tea, you just wait the more energetic atoms evaporate and go out of the system, and the low energetic atoms remain in the cup, so your whole system cools down. The same thing we do here. Here, the experimentally people reduce the trap heights so that the high energy particles which are on the higher levels, they will go outside the trap. Now this can be done in different way, like you can flip the trap and many things. But the most successful, ultimately what we got, the simple successful technique was the RF evaporative technique. Means what it is done, they apply a radio frequency waves on the system which is already trapped, and then that radio frequency field flips the spin of the high energetic atoms, and since the spin is flipped, the trap is in a way that those spins which are not flipped, they will feel a potential well, and the spins which have flipped will see it as a potential hill, and those high energy atoms will slide down the slope of the hill, and what will be left with is low energetic atoms, and thereby you will achieve cold, you will reduce the cold temperature of the system. So in this way, there was another problem with that, that as you are reducing the temperature, it has been observed that there is a hole in the trap. Hole in the trap in the sense that at the center of the trap, the uh, spins of the atoms flip automatically and they go out of the trap. So some atoms leaks. To stop that, what this Phillips and they did, they proposed to apply another strong laser beam at the center, and a circulating RF field, so that the thing is that suppose there is a hole, the atom is chasing the hole, but it is not finding the hole. So hole is moving, atom is moving, but it is not catching the hole, so it cannot come out of the trap. In this way, finally they were successful to achieve the cold temperature required for the Bose Einstein condensate. If I this is the overall schematic diagram of the experimental techniques, and these are the groups which first successfully obtained the cold temperature for required for the Bose Einstein condensate, and following that, you see this is 1997, and immediately next year 1998 in MIT, William Anderson and his group got the first BEC with rubidium 87 atoms. Now after that, several other groups like Anthony Leggett, they also obtained, and not only they obtained the BEC, they got, while Anderson obtained BEC for few few hundred atoms in the system. Anthony Leggett group got it, obtained it for few million atoms, and therefore they could perform much more measurements in the with this system. Now, why this system? So we obtained the BEC, and that immediately caught the attention. So you can understand why it took from 1925 Einstein paper predicting that there is something called Bose Einstein condensate, where you will have a macroscopic population in the ground state, in the lowest energy state. And finally, in 1995, 70 years later, you are observing the BEC experimentally. Now you achieve the BC, you have to observe it. And the observation technique is basically simple imaging, and what you do, you switch off all the traps, so the atoms will start moving, and then you apply a laser and you take the picture of the shadow, and it's amazing. You can see that you get a distribution of the velocity in the image, where at the center where velocity is 0, basically that is the lowest temperature, you have very sharp peak, and then the peak broadens as the time passes and the temperature increases. So it's beyond doubt that there is a condensation. Now we observed it. Now, fine, what Einstein said, it has been verified with clear evidence, and so that story could have ended there, but it actually opened a uh, new paradigm for the physics community, particularly working with the atomic and molecular physics and condensed matter physics, because here your atoms all are in the same quantum state. So this beam of atoms are coherent. It can be used more like atomic lasers, and that opens up with the possibility of very finite, very precise measurement of different physical quantities. So that is the first important thing. Secondly, the size of, you are taking here the image, just optical image with a camera or laser light of the quantum system, and this is a purely quantum phenomena. So this is first time we are observing the quantum phenomena with open eye. The size of the atoms, size of this BC is about a fraction of millimeter, basically the thickness of our hair. So you can see it's a quantum effect at the macroscopic scale. So you can now observe quantum phenomena with our naked eyes. And second, it's a very clean system. This atomic system has no defect like your solid state crystals or those things. And here, because these laser traps, these traps are made by lasers and magnetic fields, you can control the shape of the trap. Even the atom-atom interactions can be tuned. The strength, the sign, attractive or repulsive, everything can be tuned using the techniques of phase-back resonance. That's a different topic. The main point is you can tune the system parameter almost at you as per your wish. And thirdly, as you can see, this system is basically hanging in the space with the help of these laser lights and magnetic fields. So it is not in touch with any physical container walls or anything else. So it's basically the nearest possible approximation of the truly isolated system. So this can be used to study the non-equilibrium statistical phenomena, like how a system achieves thermalization, how it reaches thermal equilibrium. Those things can be studied here. Further, it's a quantum system, macroscopic quantum system, and it consists of many atoms. Therefore, you can study here the quantum basic quantum phenomena like quantum tunneling, the many body wave functions, their entanglement, and that's why it became as a very prominent candidate to study the quantum computation, quantum teleportation, quantum informations, and all new quantum technologies. And it has the potential to change the world the way we see it today. Now, so roughly this was the first part of my talk, and I will take maybe another 10 minutes maximum to just uh, give you a brief idea about what we are trying to do. Now, from all these things, one thing is very clear, that the system has a tremendous potential. So to use this system, whether we want to use like this optical lattice, or and we want to use it for studying the quantum information or quantum entanglement, or we want to use it for precision measurements like atomic clocks and others, we have to have a detailed knowledge about the system. very detailed knowledge at the level of the wave function. So we need to understand the system, and we need to be able to calculate its wave function and energy values as accurately as possible. Our group is trying to exactly do that. Now, any system that we want to study in quantum mechanics, we need to solve the Schrodinger equation. You have the Hamiltonian, you try to solve it. Unfortunately, here we are talking about a system consisting of from few hundreds to few millions of atoms, and each atom has 3 degrees of freedom. So you can understand the dimension of your problem. So you cannot solve it directly. Even worse, this problem has a interacting potential. So you cannot simply use your usual techniques that we usually use in our textbooks to solve a Schrodinger equation analytically for some typical problems like harmonic oscillator or square wave potential. Here we need more sophisticated techniques. Now, first approach, the first two popular methods were Gross-Pitavetsky equation and two more Bose-Hubbard model. In the Gross-Pitavetsky equation, it has been assumed that all the atoms are basically moving in a average potential. So your interacting potential will be replaced by a average potential, and in that way, you can solve it by assume when all the atoms are moving in the same potential, then the total wave function of the n particle system will be just product of the n number of individual wave functions. And then you take it as an answer, you use the variational principle, and you will be able to solve the problems, of course numerically. But the problem is that the moment you are doing it, then the interparticle interactions has been compromised, and you are also taking the interactions in this GP equation as a collision, just delta potential. That is far from the realistic case. Initial days our experiments were not much precise, so GP equation was quite successful to describe those experimental results quite accurately. But with the advent of more sophisticated techniques and more new experiments where even further precise measurements were possible, it was clearly seen that the results are deviating. So we need different techniques. The other one is, the next one was the Bose-Hubbard model. Here it's basically taking the lowest energy band and trying to get the solutions. So here you get some many body features, but not the all. So what we are trying to do is basically, instead of we are taking the answers to solve the Schrodinger equation by variational method, the trial solution we are taking as the combination of all possible configurations. So if we have n number of particles, you take the product of n single particle atom wave functions, then symmetrize it, and then you take that combination you take as the answers. In that way, we apply the variational time dependent variational method, and from that we get the working equations like this. Next, we can solve this equation by numerical techniques, and with that, we studied several experimentally realizable atomic systems, ultra-cooled atomic systems, or Bose Einstein condensate systems. One very important system is the Bosonic Josephson junction. It is called Bosonic Josephson junction because it basically mimics the physics of Josephson junction in the condensed matter physics. You have a double well. The macroscopic state is in the one well. Then it will keep on tunneling between these too well. Now there are different variations, like you can take the interaction as a finite range interaction, which is more realistic, and we have seen that how this based on the range of the interaction as a fraction of the length scale, that is the width of the well, the system behavior, the density oscillation changes. Then you can study the if the effect of asymmetry. You can never measure, you can never have a very precise symmetric well. In experiments always some asymmetric is there, Another thing is that asymmetric double well is a unit of your deformed crystal. So that effect also we can study. And then what if we have a two-dimensional structure? So that also we studied. And the dramatic and the interesting part is that when we were studying these oscillations, we saw in the experiments by a group of Smith-Meyer, they have shown that the density oscillation decays with time. That decay cannot be seen with the GP equation, the left-hand side one. However, we could show with the taking the full many-body wave function, even with the approximations, with the precision that we could achieve, we could at least demonstrate that experimentally observed feature of decay in the oscillation. And so this is where I would like to stop, because I think it's and about the future work, we are trying to develop the linear response theory to get the excitation. And as I said, that we are also planning to study the quantum entanglements in collaboration with Professor Aditi Dey. So here I would like to stop. Thank you for your attention.
Okay. Thank you, Sudip, for such informative talk. And I'm sure those people who are watching us now and later on when they will be visiting the lecture, I'm sure they will get benefited. Very simply, you explain the phenomena of both Einstein condensation and updated up to what is currently going on in the field. And now it is time for some question answer session. So I would like to ask the people who are joined us to put their question in the comment section. And for some of that, we will take for this session. Till we get some questions from the student side, uh, let us talk about a little bit. I'm also not uh, expert in the field. I haven't worked in the field, so I'm familiar with this Bose Einstein condensate this phenomena, and I would like to ask you that sometime we heard a lot about quantum communication entanglement and all, and there we used to sometimes trap atoms by laser trapping or something. So how this quantum communication and both Einstein conversation is related? Can you put some light on the perspective of?
Actually, as I told already, the basic idea is that in quantum computation or quantum information, the basic ingredient is a entangled state. Okay,
Yeah.
so you
Mhm.
need a system where you can prepare a entangled wave function. Now, to experimentally test your proposition, you need a system where you have enormous control. You can control almost every bit of the system, and BC is a very clean system. Okay, and also you see the when I showed you the active wave function, the answers, you see that it's not just a product of the wave function, it's a correlated wave function. So this system has the potential to offer you a entangled state where you can control the state as per your requirement, and then you can use that entanglement for your purpose of quantum computation or whatever you want.
Okay.
So the
Okay. Thank you.
idea, so the point is that here ultimately you want a entangled state, and this
Right.
system is offering that entangled state. After that, it's a different story. That's how
It's
these two
different.
are merging.
Yeah. Okay. And I have one question from a student that what is superfluidity? So the superfluidity is some.
Superfluidity, I think it is uh, um, it's quite general thing. I mean, it's a so what happens if you lower the liquid helium? Around 3
Mhm.
Kelvin temperature, there is a phase transition, lambda phase transition. So what happens? Suddenly the viscosity, surface tension, all goes to zero basically. So you have a normal fluid behavior above 3 Kelvin, and below 3 Kelvin suddenly you have a different behavior. You don't have the normal fluid phenomena. So that is that phenomenon. It's more like superconductivity. When below a critical temperature
Yeah.
your resistivity goes to
Yeah.
zero, you can practically can have infinite conductivity. So that is same in case of liquid
FoP.
helium. And this is actually in lambda transition in Bose distribution chapter in PG. I think it is taught little bit.
Yeah. Okay. So there is one more question about this discussion, that the people who are undergraduate or postgraduate students in the different institutes like ours. So many people have a lot of interest for research. So somebody who is into research, who want to do research, so they generally tend to know from teachers or researchers active in the field, that what should be the way to approach if somebody is interested in this low energy physics. So what are the places in India they can aim for?
Okay. In India, if we talk about the opportunities to do research in the cold atomic system, experimentally there are very few places. Okay, as always, India is not a rich country, and such sophisticated experiments needs lot of funding, lot of physical infrastructure, manpower, which we cannot afford. But still, there are definitely certain places where you can do the. First, I am telling the experimental part, then I will come to the theoretical part.
Yeah,
So, of course, in the experimental part, there are few places like Raman Research Institute in Bangalore, TIFR, of course. Actually, TIFR in TIFR, Professor Unnikrishnan group is the first group in India to achieve the VEC. Apart from that, in Raman Research Institute, there is a cold atom group, so where I don't think they achieved the BEC, but they achieved quite low temperature of the micro Kelvin level, and they do all the precision measurements kind of things. So there is one group. In ISS Kolkata also, I think there is a experimental group. Earlier, Manos Mukherjee was there. Now he moved to National University of Singapore, but still I think there is some laser cooling facility. And in my university, of course, in Calcutta University, there was a group, Professor PN Ghosh's group. He has retired, but his other faculties like Vishwarup Ray and others are there. So we also there had a laser cooling facilities where you can study the cooled atoms. Now coming to the theoretical, there are a lot of theoretical research in India. There is no problem, absolutely. Even one person sitting in any institute can do this research. And if you see, for example, now one of our friend Lalit, you will know Orko is, I think, in
yeah,
IIT
I'm not
Mandi or IIT. He works on
I think
these
only, yeah.
things. Yes. Then Dilip Angam in PRL, he works on it. In HRI, there is a very big quantum information group. Then Amit is there in IIT Dharwad, I think, who also works on this quantum information and cold atoms. So in theoretical, lot of people
Yes,
are
yes.
there. Krishnendu
Lot of
Sengupta in
people.
ISCS, he is a Bhatnagar winner. He also works on this. A lot of people works on it. And of course, in abroad there are places. So now, depending on your interest and what kind of effort you are putting and what kind of situation you are facing, you have to choose. If you have the
Yeah,
opportunity to go abroad, and then you have to prepare for that. Like in USA, you have to clear GRE and TOEFL for good universities. In Europe, there are many countries where GRE is not that much important, but you have to approach them individually and see if the funding is available. And in India,
yeah,
of course, the method is quite standard, and everyone knows that you have to write CSIR net or JEST. And if you can crack either of these two, you will get a handsome scholarship, and you can approach these research institutes or IITs, central universities, and you can work with a fully funded PhD basically. But for
Yeah,
that, of course, you have to come in that top creamy layer, because CSIR net almost only 2% I think get the JRF,
yeah,
and just also, and maximum 200 people qualify. So you have to you have to
it's
prepare
a work.
from your semester one. You cannot the plan when you are in the final semester, then it will be very
Yeah,
difficult. But if you plan early,
that is important.
starting from first semester, as you are studying your first semester materials, that same time, the question papers are available in the market. You just go and buy a jam 10 years question paper book, and when you are being taught in the first semester mechanics and GPM in the BSc, at that time you start solving those problems from those chapters and keep in the notebook. So before
Mm.
exam you can just go through it, and you can try. But planning, because lot of students are there, seats are limited, so competitions are there, planning is required for sure.
Yeah, yeah. So that is, thank you for this clearly setting the way these undergraduate or postgraduate students can look forward, those who are interested in research. And now, Sudhir, I have one. I just want to take one comment on one of my questions. That
Yes, yes.
recently we see from last few years, we see a lot of fund cuts in research, and almost private institutions are struggling to get funds for research. And research infrastructure is really a thing which we need to think of how to uh, do good research while sitting in a private institutions
It's
in India.
actually, I understood the point. It's really a very pity situation in India, not only in private institutions, even among the government institutions. If you are out of that creamy institutes, those fortunate and pampered children of our government, these research institutes like HRI, TIFR, or you don't have any person attached to you who are working there and lend their resources to you, it's very difficult to work in India. And
Yeah,
particularly in universities, if you look at the regulatory framework of our country, I am really frustrated after coming back that this regulatory framework demands that you do good research. Then they are asking you to take 16 to 18 hours of teaching, and then they
mhm.
want you to maintain all the documentation for your NAC accreditation, UGC, NBA, and all those things. Now, and then, so forget the private institution. Even within the state government
It's all.
universities, how many universities you can say confidently that yes, good quality research is done there? Even within the IITs, there is not much uniformity. The kind of quality of research, if you say that in the old IITs, IIT Kanpur,
The
Bombay,
seven IITs
Chennai,
were very poor.
yes, and if you come to the new one, there is a lot of divergence. And even in the ISERs also, so that is the problem. And when it comes to the private university, it is another hell, because if we leave aside this 5 6 again, this pampered child of the industry bodies, funding becomes a very difficult question. Now everyone,
And working in fundamental sciences is always again one more challenge. There's somebody
yes,
who
actually,
can go to industry.
actually, if
The
you see,
fundamental
if you
sciences can
see,
go to industry as a research.
yeah, actually, if you see last 10 years, the focus of our government also has changed. They want more industry oriented research rather than
Yeah.
fundamental problems. They are working in the line more like China or South Korea, where engineering projects get much more priority than okay, that has, again, the problem comes with the limited resource. When you have 100
Yeah.
rupees, you cannot buy everything. No, you have to prioritize.
That is.
But problem is that we cite US and other European countries, or not European, say Korea, where private universities are doing very good. We always say Harvard, Princeton, and all those universities are basically private universities. Even in South
Mm.
Korea, Postech is private university, and it's among the world top 50 young universities. Then why not in India? Now, if you see, look at the ecosystem in USA or South Korea, there is a level playing field among the universities. In India, we don't have. Like we are operating in Delhi NCR, where there are a lot of government institutes. They are running with ad hoc faculties, but they are offering practically free education. Now, given the economic situation of our country, recently you see this economic advisory panel to the prime minister. They said that only 10% of our working population earns more than 5,000 per month. In that situation, how can you expect a student to study physics honors in a private university, paying lakhs of rupees, where they don't have any assurance of job? So that becomes a
Yeah, so that
problem
is that
to
is a lot
operate.
of things, and the
Government
importance of fundamental science is something at different level, and the bodies or the think tank who think about this. The
see,
fundamental
I
science has its
in
own
my in my
purpose.
opinion, there is only two ways. Either you run a government system, or you follow completely the US pattern, where there will be level playing field between your government and private bodies. Everybody will be forced to earn their revenue, and the subsidy to the poor students who cannot afford to pay the tuition fee should go directly to them, not the present system, where at one point government is running universities without almost any infrastructure and free, and the other side, you there are no students who are struggling to pay the tuition fee. So better you make the tuition fee uniform and give the scholarship to the students so that they can afford it, like in US and others. Only then there will be uniformity in the resources and competition, and everyone can grow. Without funding you cannot grow.
Yeah, so
But
that is,
so
and
that
we are
problem is there.
almost we are like on the receiving end of this system. So there is
Yes.
a lot of fundamental science. We're doing fundamental science,
Only
and we are at the
regarding the
receiving end.
funding, I think only this DST tier is the new proposition that is helping private institute faculties a bit to get some easy fund. So that is only thing directed. The other things it's very difficult. Even government also you will not get unless you are in the top tier institutes. It's
Governments
there are
are also cutting a lot of funds for research. So there are a lot of
yeah,
fund cut from recent
it's not
years.
new. It's happening for last 10 years. It started
Yeah,
during the
yeah,
UPA
this
2
is-
only. We were at
yeah,
PRL that time. This all problems started.
yeah. So now things have much changed at PRL also.
Yeah, yeah.
Uh,
Yeah, they also have in ISERs. I was speaking to Ujjwal and he was telling that there are a lot of limitations now how to use those resources. So very difficult now. No, not much
yeah,
freedom like earlier.
this is quite challenging. But at the same time, like we are discussing about this Bose Einstein condensate and this Indian scientist who did wonderful job at that time when India was struggling with a lot of things as well. So we
Yeah, yeah.
keep our hopes high and we'll keep on working. And I'm sure that in future we will do
in
something
in this
better.
way connection, I just want to have a comment that what we are today discussing about this funding and this, actually there is a paper by Arnob Raichaudhuri. He was a
Mhm.
professor in IISc. The paper titles is the epoch of Indian physics. It is written in the context of the this legendary batch of people, Meghnad Shah, Satyen Bose, who all were at that time in Calcutta University, and there he discussed how lack of support from the authorities, that time British government, and lack of funding ruined that initiative. That was the world level initiative. Na? In every field we had groundbreaking work,
Yeah.
starting
Yeah.
from Shah ionization to Raman effect, Bose Einstein condensation, everywhere, but it could not carry forward. So that is a nice article. If, you will get a idea how lack of support from
No,
the system ruins everything.
yeah. Okay, Sudip, so thank you
Okay.
for taking time for us and very interesting discussion. I'm sure that things will improve in future and we will continue our engagement. We will keep on meeting on other occasions as well. So thank you so much for being here, and I thank all the participants who have joined us. and later on we will be listening our lecture on YouTube. So thank you so much. We will be back with another speaker in the series with a new topic. Thank you. Thank you so much.
Welcome.